Assalamu alaikum. Welcome to the next lecture. In this lecture, we'll try to do a numerical, and it may cover all the topics which we have covered till now. So this numerical reads like this: a line has a characteristic impedance of 400 ohms, and the resistance connected at the receiving end as 500 ohms. Assume that the magnitude of forward traveling voltage and current waves are 5000 volts and 12.5 amperes respectively. Determine the following: reflection coefficient of the voltage wave, that is alpha v, reflection coefficient of the current wave, that is alpha I, backward traveling voltage, that is VB, voltage at the end of the line, that is V, refraction coefficient of the voltage wave, that is alpha V, refraction coefficient of the current wave, that is alpha I, backward traveling current wave, that is IB, current flowing through the resistor, that is I. I think this is the reflection coefficient of voltage wave, that is beta V. This is the reflection coefficient of the current, that is beta I. So I'll start from beta V. Beta V, as we know, that's equal to, in case of the line terminated by a resistance, that's R minus ZC divided by R plus ZC, where R is 500 minus 400 divided by 500 plus 400, that is 1 by 9, that is 0.1111. So beta I is minus times of this. We know that the relation, that is minus 0.1111. VB is the backward traveling voltage, that is R minus ZC divided by R plus ZC into VF, that is beta V into VF, that is 0.1111 into 5000, that comes out to be 555.55. Similarly, this can also be calculated like this. Voltage at the end of the line, that is V is equal to VF plus VB, that is VF is 5000, V is 555.55, that is this much voltage. This can also be calculated like this: twice R divided by Z plus R plus ZC into 5000, that is 2 into 500 by 900, that comes out to be 5555.55 volts. Refraction coefficient of the voltage, that is this twice R divided by Z plus ZC, that's 2 into 500 divided by 900, that's 400 plus 500, that is 1.1111. Reflection coefficient of the current is this, twice Z divided by this, R plus ZC, that's 2 into 400 by 900, is 8 by 9, that comes out to be this. You can see this plus this is equal to IB is equal to minus R minus ZC divided by R plus ZC into IF. It is equal to minus 0.1111 into 12.5, that is equal to minus 31.3889 amperes. I is equal to V by R, that is 5555.55 divided by 500, that's 11.11 amperes. So you can calculate this by using that relation also, that is this: I is equal to twice ZC divided by R plus ZC into IF. That will also come out to be same, that is 2 times 400 divided by 900, that will be same, that is 800 by 900 into this. You will see that will be again the same. Now let us see, when the line is connected to the cable, that is Z is the characteristic impedance of the cable. When this happens, we know that the refraction coefficient of the voltage will be, that is Z twice Z divided by ZC. ZC is the characteristic impedance of the overhead line, and Z is the characteristic impedance of the cable. We know that the characteristic impedance of the overhead line is 400 and for the cable is 40. So this comes out to be equal to, it means that ZC is equal to 400 and Z is equal to 400. So ZC divided by Z plus ZC into VF, that is equal to 2 times 40 divided by 400. 40, it is 80 by 400, that is only 18% incident wave. So this cable has reduced the voltage up to 18% of the actual wave. That is for this reason that an overhead line is usually terminated near the station by connecting the station equipment to the overhead line through the short length of the underground cable, because it reduces the voltage surge to only 18% or by 82% of its value. Because of the presence of the capacitance, steepness is also reduced. So because of the lower characteristic impedance, it reduces the magnitude of the surge reaching to the junction, and because of the capacitance present in this cable, it reduces the steepness of the wave. Now the reflection and refraction of the T junction. Until now we have simple junction. Last we have only one line, that one in Z2. Now let us say we have another line which is connected between Z1 and Z2 like this. So some books show it like this, Z1, Z2 and Z3, but electrically they are like this. That is Z1 and Z2 and Z3 are in parallel. So this will be similar to that of the earlier case. This is the junction where these two are connected in parallel, and we can see that these are two impedances, and this is the junction, and the equivalent of these two is the parallel combination of this. So alpha v will be equal to 2 into z2 parallel z3 divided, that is actually twice z divided by z1 plus z, but z is here, z2 parallel z3, that is 2 into z2 z3 divided by z2 plus z3 divided by z1 plus z2 z3 divided by z2 plus z3. So by simplifying it, this remains as it is. So it will be z1 z2 plus z1 z3 plus z2 z3 divided by z1 z2 plus z3. This z2 plus z3 will cancel out. It comes out to be twice z2 z3 divided by z1 plus z1 z2 plus z2 z3 plus z1 z3. Now I will divide numerator and denominator by the multiplication of z1 z2 z3. Z2 z3 cancel out. It comes out 2 by z1. Here there is no z3. It will be 1 by z3. Here there is no z2. It will be 1 by z2. Here there is no z1. It will be 1 by z1 as we divide it by z1 z2 z3. This is an important result when we have a T junction. This is the refraction coefficient of the voltage. Similarly, we can get the refraction coefficient of the current, that is this z1 minus z1 divided by z2 z1 z minus z1, and z is the z2 parallel z3, and this is z2 parallel z3. So when we put the value and simplify it as we had done earlier, it comes out to be 1 by z1 minus 1 by z2 minus 1 by z3 divided by 1 by z1 plus 1 by z2 plus 1 by z3. Now let us see at z3 we have a capacitance C connected between this junction and the ground like this. This Z3 is a capacitance. Let us see what is its behavior, and we say that Vf, that a forward voltage wave, is a sort of a step voltage as we have discussed it earlier. So Z3 will be equal to 1 by omega c, and Z3 in S domain will be equal to 1 by Cs. So V is equal to twice Vf by Z1 divided by 1 by Z1 plus 1 by Z2 plus 1 by Z3. So Vf, since this is a step function, its Laplace will be equal to Vf by S. So that's why I have written Vf by S. So twice Z1 into Vf by S is 1 by Z1 plus 1 by Z2 into Cs. Let us try to simplify it. This will be equal to Z1 plus Z2 divided by Z1 into Z2 plus Cs. I will divide C numerator as well as denominator. It comes out to be Z1 plus Z2 divided by Z1 Z2C plus S. Here it will be equal to twice Vf Z1 into Cs. That is here twice Vf S into Z1 into C into 1 divided by Z1 plus Z2 divided by Z1 Z2 into C plus S. So I have done this simplification to get it over here. And let Z1 plus Z2 divided by Z1 Z2C is equal to alpha. That means this term will be equal to alpha. So this term will be equal to twice Vf divided by Z1C, twice Vf, it should have been Vf divided by Z1C divided by, this is S, this is alpha, that is alpha plus S or S plus alpha. This is the last term which we have calculated. Now this I can write it like this, twice Vf divided by Z1C into 1 divided by S into S plus alpha. So V of S will be equal to twice V by Z1C. I can partial fraction this. So this will be equal to, when I again multiply them, S plus alpha minus S. When I simplify it, it will be S plus alpha minus S. S and S will cancel, but alpha remains there. That's why I have done divide by alpha. Or we can say we get the coefficient of this will be equal to 1 by alpha. Coefficient of this will be equal to minus 1 by alpha. So when I put the value of alpha, that this equal to Z2 plus Z3 divided by Z1 Z2 into C, Z1 Z1 cancel out, C and C will cancel out, it will be equal to twice Vf Z2 divided by Z1 plus Z2 into the Laplace transform of this will be equal to Laplace inverse transform of this will be equal to 1, and for this it will be e raised to minus alpha t. So this is the voltage variation of this at the junction, So it will vary like this. The maximum value will be equal to twice u of z2 divided by z1 plus z2, and it is given by this equation. You can see, of course, the variation will be very slower depending on the value of the capacitance. We have assumed in the derivation of expression for the voltage of the capacitor in the previous section that the traveling wave surge is of the infinite length, that is the step length. But now, in fact, as I have told you earlier in the beginning of this, that the traveling wave are of short duration. So we'll now let us derive the expression when the surge is of the finite duration, let us say of tau. See, also let the magnitude of the wave be equal to vf volt. So we can show it like it's a step function, but only of, you can say it is a pulse type, only of tau duration. So it is given like this. So this v of t will be equal to v of ut, that is unit step, minus u of ut minus tau, another unit step which started from at this point. So when whole of the unit step is subtracted, when whole of the step has been subtracted this, we can get only this much of the pulse. So u of t is equal to vf for t is greater than 0, and this is equal to 0 for t less than 0. So vf u of t minus t is equal to vf for t greater than tau, and this is equal to 0 for less than tau. So when we subtract it, we get this value. So it is Laplace will be equal to v by s minus v by e raised to minus tau. This is the property of the Laplace transform. So the voltage across capacitor will be twice vf. There will be now two terms. This coefficient will be same, only this will be different. So when we simplify it, you can see that we get, for this we'll have this term, the earlier one, and for this we'll get the similar term, only this t will be now shifted by tau. That is the shifting property of a Laplace inverse transform. So this is its variation of the voltage with respect to t. And its maximum, you can see, will be at t is equal to tau, and that it reduces again. You can see it reduces again. So let us see what is its maximum value when t is equal to tau. You can see when t is equal to tau, this comes out to be 0. This e raised power 0 will be 1, 1 minus 1 will be 0. It will be equal to twice v of z2 divided by z1 plus z2, 1 minus e raised power alpha into tau. It will be its maximum value. The maximum value will appear at t is equal to tau, and v max will be this, which is clearly less than twice v of z2 divided by z1 plus z2, which was the earlier case in which we have assumed voltage to be there for infinite time. So it is therefore clear that the attenuation, that is decreasing the voltage, in the magnitude of voltage for a short wave is much more rapid than for a long wave. It is rapid, and also it makes its magnitude is also less. The effect of the shunt capacitor is to reduce the steepness and the magnitude of the wave reaching an increment. So the shunt capacitance will try to do what? It reduces the magnitude, you can see, and it reduces the steepness of the voltage. You can see the steepness of the voltage over here almost instantaneous. Since the inductor is the dual of the capacitor, an inductor in series with the line should give the same effect. So that is this. Until now we have assumed this capacitance in parallel with this. Now this, the inductance in series with this, will give the same effect. In this case, when we do this kind of analysis, z2 will be equal to z will be equal to z2 plus s into l, and then derive the equation for alpha v, that will be equal to z2 plus twice z2 plus sl divided by z1 plus z2 plus s into l, and then you can go accordingly, and you will see that the output equation will be equal to twice z2 plus z2 divided by z1 plus z2 into vf, that is 1, and output will be 1 minus e raised power alpha t, where alpha is equal to z1 plus z2 divided by l. So I hope you can do this on your own for series inductance, because the effect of series inductance and the shunt capacitance is same. You can see the voltage variation will be same, and the maximum value also will be same. Only difference will be the alpha will be slightly different, because in earlier case it was equal to z1, what was this z1 plus z2 divided by z1 z2 into c. Here it is z1 plus z2 divided by l. So you can derive it. Only consideration is that now the z, that is termination, will be equal to z2 plus sl, and in case of capacitance it was the parallel combination of z1 this z2 z3, parallel combination of z2 z3. So this is very simple. So alpha v will be equal to 2 times z2 plus sl divided by z2 plus sl plus z1 into v, that is vf. You can use that and then derive it. Now we will try to do numerical on the same equation. An inductance of 800 microhenry connects two sections of the transmission line, each having a certain impedance of 300 ohms. That means Z2 is 300 ohms and Z1 is 300 ohms, 350 ohms. Sorry. A 500 kilovolt 2 microsecond rectangular surge travels along the line towards the inductance. Determine the maximum value of the transmitted wave. The maximum value of the transmitted wave will be, of course, at alpha is equal to that value, because this is derived for the long transmission line. You can derive its derivation will be similar to that of this. Now Vt is equal to Vf. Now first we'll calculate here, simplify this. Since here Z1 is equal to Z2 is equal to Z, so this will be equal to twice Z, this will be twice Z, this and this will cancel out. It will be equal to Vf 1 minus e raised power minus alpha t. Actually it should happen like this: twice Vf 1 minus e raised power minus alpha t minus 1 minus e raised power minus alpha t minus tau, because it is a pulse. Here tau will be equal to Z1 plus Z2 divided by L. It will be equal to twice Z by L. It will be equal to twice Z by L. Now at t is equal to tau, this relation comes out to be like Vmax will be equal to this twice it will be Vf 1 minus e raised power minus alpha tau. So this will be equal to, this will be alpha tau. Tau is equal to twice Z by L. Z1 is equal to 2. So 501 minus e raised power minus 2 into 350. That is 2 into 350 divided by 800 microhenry. So it comes out to be this value. So when I put tau is equal to 2 microseconds, so V is equal to 500 into 1 minus this, it comes out to be 413.5 kilovolt. In this way we can calculate its value. Now the restriking voltage. This is an important thing. What is the restriking voltage? We know that whenever the circuit breaker opens or any switch opens, a voltage appears across its terminals. So that voltage which appears across the terminals of the open switch or open circuit breakers is known as restriking voltage. And when we need to derive the voltage, this expression for this restriking voltage, and see whether this restriking voltage will try to close this switch on its own or not, because if the voltage magnitude is more, it will make this air conducting by breakdown the air between the two contacts. So we have to be very careful in that case, because for high voltage this is an important aspect. Let us say we have a simple transmission line where it is considered to be lossless, and this is the shunt capacitor, this is the series inductance, and it is supplied by an AC source Vm sine of omega t. So this is usually required to determine the voltage across circuit breaker during the opening period, because in the opening, as I have told you, opening period, the more voltage magnitude, the more that voltage magnitude will appear across the circuit breaker terminals. There are certain assumptions. Let us say the fault is solid, that is there is no arcing, and solid fault means there is no impedance connected between neutral and ground. The magnitude of positive impedance is assumed to be constant. It may vary because of some other effects, but here we are assuming them to be constant. Effect of corona and saturation is neglected. All the charging current before the fault and the load are neglected. Before fault and the load currents are neglected. The current interruption takes place at the current 0, where voltage passes through the maximum value. Current interruption means that the circuit breaker opens when the current passes through the 0, because when the current changes in the AC circuit, it passes through 0 twice in one cycle. So we assume that this current interruption or circuit breaker opens when the current becomes 0 at any instant of time between the cycles. System is lossless, which I have shown here. Here there is no R present. Now the fault current IF is equal to V by Vs by Zs, that is Vm by S, and we assume that this Vm is constant. We are not using this sinusoidal. We are using only the instant at which the voltage is maximum, because at that time current will be flowing through the 0 value. So the fault current Vm by S into the impedance will be Ls, because the fault will be flowing through this circuit. Vm is taken here because fault injection takes place at Vm. Impedance seen by the circuit breaker. Now impedance seen by the circuit breaker is the parallel combination. You can see it from here. Impedance seen by the circuit breaker is the parallel combination of these two when it is open circuited. So impedance seen by the circuit breaker is ZL cross ZC divided by ZL plus ZC. So ZL is LS, that is 1 by CS, LS plus 1 by H is equal to LS divided by LCS square, which is 1 by C, S divided by S square plus 1 by LC. So voltage across circuit breaker will be equal to IS into Z naught, that is the total current multiplied by its impedance that is seen by this, because the current flowing through this will be the short circuit current. So IS is equal to Vm by S into 1 by Ls into 1 by CS divided by S square plus this. So this S and S will cancel out. Vm by Ls, sorry, LC. Here it will be Vm by LC. Yes, it will be Vm by Ls, not LC. Yes, it will be Vm by LC. So L into S. L into C will be over here, and S is multiplied to this part. That is, it will be equal to Vm by LC, S into S square plus 1 by LC. So this comes out to be like this. So when we partial fraction it, it comes out to be S square plus 1 by LC minus S square. S square S cancel out. There will be 1 by LC over here, and that 1 by LC and this 1 by LC will cancel out. It comes out to be Vm 1 by S minus S divided by S square plus 1 by LC. So its value will be equal to the Laplace inverse of 1 by S is 1. Laplace inverse of this is cos of omega naught t, or you can say cos of 1 by root of LC into t, because here we can represent by some omega naught square. It will be equal to S square, S divided by S square plus omega naught square. So it will be equal to Vm 1 minus cos of omega naught t, that is where omega naught is equal to 1 by root of LC. So this is an important result. From this we can calculate what is the maximum voltage that is appearing across a capacitor. This is the value of Vm. So at t is equal to, it has its first peak at t, omega t is equal to pi. When omega t is equal to pi, this comes out to be minus 1, minus plus, that is twice Vm. So omega naught t is equal to pi, that is t is equal to pi by omega naught, that is this, and t is equal to, when omega naught is given the value 1 by root of LC, pi root LC. So the value of this voltage of the circuit breaker at t is equal to is twice Vm. So we can see here not only Vm, which is the input voltage maximum. So the voltage across this, the voltage across the circuit breaker when opening of this will be equal to twice the voltage that is appearing as a source of this. This is not that source which is generated voltage. This may be some transient also. This may be some other parts also which can have this Vm more than very high as compared to the normal operating voltage. So we have to design our circuit breaker with respect to this voltage twice Vm, and we have to first devise what is the value of this Vm. So here this Vm is known as the restricting voltage, or this total is the expression of the restricting voltage with respect to time, and this restricting voltage is the maximum value at t is equal to pi root LC, and that value is equal to twice Vm, and the circuit breaker finally should be designed on the basis of twice Vm. I will stop here. Thank you.